The universe as we know it now is a very structured universe. There's galaxies, there's stars, but it has not always been like that. We would like to study the period that formed the universe that we can see now. We can see the light that was emitted billions and billions of years ago, only at the lowest frequencies. So we need a low-frequency instrument. LOFAR is a low-frequency radio telescope, and it's actually the world's largest radio telescope.
LOFAR is a giant network of radio antennas spread across 8 European countries, built by Astron in the Netherlands early in this millennium to catalogue some of the objects in the early universe at the lowest radio frequencies.
We have the low-frequency antennas ranging between 10 and 80 megahertz, and high-band antennas between 110 and 260 megahertz. Every station of LOFAR consists of many of those antennas.
What makes LOFAR absolutely unique compared to previous generations of radio telescopes is that it has a very large number of simple, lightweight antennas, and all of the smarts is in computing.
Every antenna of LOFAR is sensitive to the whole visible sky. We add the data of all the antennas in software. By making use of the geometric delay, we can actually steer the beam of all these antennas to point to a certain direction in the sky.
Because LOFAR is a software telescope, you actually have the ability to either get a nice atlas, or to get a nice image of a part of the sky, or to study one object in very exquisite detail.
There's been nothing else that is so sensitive, so can look so deep into the radio sky and get images that are so sharp. It has already revolutionized radio astronomy.
Since LOFAR pretty quickly established antenna stations in several countries, we established as Astron the International LOFAR Telescope. That entity runs the entire facility to the benefit of astronomers around the world.
Since start of the operations in 2011, we already collected 35 petabytes of data. Only a small fraction of the data has been analyzed so far.
There are many processes that go on in the universe that emit radio waves at those frequencies that are very poorly explored. This starts from the sun, then on to magnetic fields in galaxies, black holes, back to the epoch reionization.
We already have many very interesting results. For example, we observed pulsars, fast rotating pulsars, but also the slowest rotating pulsar. We have the lightning data, so we actually see how lightning forms over the Netherlands.
We are looking at radio sources in galaxy clusters, millions of light years across, that are particularly bright at low radio frequencies, and they are produced by shock waves. These shock waves accelerate particles in magnetic fields, and nobody understands how that works. Before LOFAR came along, maybe 20, 30 sources were known, and now we are discovering them almost on a daily basis.
We're looking at the 21 centimeter hydrogen line, so we expect to see the cosmic dawn at the low frequencies, the low band antennas, and the epoch of reionization at the high band antennas.
At LOFAR we're also investigating sources of gravitational waves to see what astronomical objects have produced these events. Learn about magnetars, neutron stars, and very exotic phenomena in the universe.
LOFAR is a major facility, and as such it is always evolving to remain at the very top. For that we have just defined a major upgrade program that we have called LOFAR 2.0.
A major difficulty for low-frequency radio astronomy is the ionosphere. We want to make use of the solutions of the higher frequencies and use those calibrations to correct the data in the low frequencies. And the way we want to do that is to triple the hardware such that we can actually read out simultaneously high-band antennas and low-band antennas.
LOFAR, of course, is first and foremost a radio astronomy instrument. But at the same time, we want to make sure that our results have as much societal relevance as we possibly can. And that's where space weather comes in.
The LOFAR for Space Weather project is to form a separate beam to continuously monitor the sun or monitor the solar wind.
So far, LOFAR has been very successful in serving the sky between 100 and 200 megahertz, but pushing down to the very low frequencies will require LOFAR 2.0. There are going to be a lot of exciting things lurking in those images that we probably can't even think of. In LOFAR, we're just now preparing a release of data. In that portion of the sky, we've discovered 300,000 radio sources. Understanding that part of the high-energy universe, this is just one of the many aspects where LOFAR is going to break ground.
LOFAR at the moment is without a doubt the premier low-frequency radio facility in the world. And now we are taking great strides to LOFAR 2.0. That will be a fantastic instrument for early universe research, all the way close to home to space weather research. It's that enormous range that really excites me about LOFAR.
It might not be so obvious that in the middle of this beautiful field, some of the most interesting science is being developed. The Pierre Auger Observatory is a 3,000 square kilometer array of detectors that 17 countries and 300 physicists built to try to understand the origin of the highest energy particles that we've ever observed.
Cosmic rays are particles which arrive from the universe continuously on Earth. Right in this moment, through my hand, you have several per second. The one that we are interested in the Pierre Auger Observatory, have 100 billion times the energy of these normal cosmic rays that are passing through my hand. The problem is that it's very difficult to find an explanation of their existence. It's very hard to find a physical process that either generate or accelerate particles at this enormous energy. So what we try to do here is to find their origin. But ultra-energy cosmic rays are very rare. You would have to wait 10,000 years to have one landing on a baseball field. So this is why you need a giant observatory like the Pierre Auger Observatory.
The reason we use this area is because it has the perfect height. It's a very flat region, and the population is very friendly to us and is able to let us into their land to leave our detectors.
Nosotros somos técnicos electrónicos, Oscar y yo, y lo que hacemos es el mantenimiento del detector en el campo y que esté funcionando. O sea, años atrás lo que hacíamos era instalar la electrónica y ahora lo que hacemos es mantener y que el detector esté funcionando, o sea, que esté enviando datos de los eventos de rayos cósmicos que está recibiendo. Le llama mucho la atención el hecho de que hayan estos detectores en el campo, que no están conectados a nada, que tienen un panel solar, que tienen agua adentro. Les llama mucho la atención de saber qué es lo que para qué funciona, para qué es todo esto.
Well, the Pierre Auger Observatory is unique because it puts together two different detection techniques. One which is based on the measurement of particles at ground, so you have 1,600 detector tanks placed over an area of 3,000 kilometers. And you have 24 telescopes that look at the fluorescence light which is emitted by these ultra-high-energy cosmic rays in the atmosphere. So the two systems work together in this way. Once one of these cosmic rays arrives from the top of the atmosphere, it produces a shower of particles detected by the surface detectors. In the meanwhile, the shower produces fluorescence light, which is measured by the fluorescence detector.
The ground detectors measure very carefully the time of arrival of the particles. And you can imagine if we have two tanks separated by a mile and a shower of particles, it's really a flat pancake comes down. It'll hit this detector first and this one later. We measure the time difference and do a little trigonometry, and we have the direction of the particle.
The fluorescence detector is a telescope which concentrates the fluorescence light into a camera. Basically, you make a movie of what is happening in the sky, but it's a very fast movie because we make pictures each tenth of a millionth of a second. This is actually an image of one cosmic ray shower that has been recorded by the fluorescence detector. The signal that we measure is proportional to the energy deposited by the shower in the atmosphere, so to the primary energy of the cosmic ray. When you put this information together with the ground detector, we are able to explore the origin of this ultra-energy cosmic ray.
Nice, that's a high energy. Auger is finally reaching the point that we can look at where these particles actually come from. And it seems to be that they are coming from these huge jets coming out of the centers of galaxies that we call active galaxies. Right now we have about 30 events that seem to correlate with the positions of these active galaxies, which have a pattern in the sky that looks like the pattern that we're seeing. So we're starting to be able to peek at the beginning of these high-energy cosmic rays, which are much, much stronger than any accelerator we are able to build on Earth. So we're getting to the exciting point right now.
Creo que turísticamente a la gente le sirve mucho, le sirve mucho.
Eso ha ayudado al crecimiento de Malargüe y al conocimiento en el mundo de Malargüe, porque antes no era muy conocido, era un pueblo muy chico. Ahora ya se conoce, digamos, en todo el mundo.
Ultra-energy cosmic rays allow us to open a new window in the universe, a window that has never been explored before.
Connecting the highest energy particles with the universe as a whole is a very interesting quest for us because we learn from both sides. We learn how nature can produce these particles, and we learn how probing these particles gives us new information about the nature of the universe.